We've been learning that for every object moving on a circular path, there must be some unseen force, the centripetal force, keeping it, maintaining that circular path. But in the case of a car driving around a racetrack, what is causing the centripetal force? If you looked at the car on the racetrack edge on, instead of from overhead, from that bird's eye view that you saw in the first slide, you would see the car coming out of the paper at you and going back into the paper away from you on the opposite side. You would notice in this exaggerated view that the curve of the racetrack was actually banked. We're going to zoom in on one portion on this side and look at all the forces that are acting on the car on that portion of the banked curve. Let's think about forces that we know are acting on this car. Of course, there's the unavoidable, always present force of weight, which is pointed straight down toward the center of the earth. That's the force of the weight on the vehicle. And then also there's some sort of a support force from the ground that's going to be perpendicular to this surface of the ground. It's pointing up this way, and that is, of course, the normal force pointing upward. What we're really interested in, though, is that centripetal force pointing toward the center of the circle. Well, where was the center of the circle? It was toward the middle of the racetrack. So we need an axis pointing that way, so let's put one there. That's towards the center of the racetrack, which is, right about here is the center of the racetrack, okay? So we put an axis there, and of course, if that's going to be kind of our x-axis, we need a y-axis perpendicular to that. So let's just put a y-axis on there, this blue line. There's our y-axis. And you notice that, of course, we do have one force that is pointed along an axis. That's our weight force. And we have another force that is pointing not along an axis. That is a normal force. So what in the world could be causing our centripetal force? I don't see a force pointing along the center of that circle or towards the center of that circle. But guess what? It is a component of the normal force. We can break our normal force up into its components by dropping a perpendicular line to the x-axis and looking at the component there. So let's see if we can make this line a little bit more evident. Line right there is our x component of our normal force. That's going to be our centripetal force. Every vector has two components, an x component and a y component. In this demo, we of course have already looked at the x component of the normal force vector. That x component is the centripetal force. The y component is the green vector that's being drawn, and the green vector, that y component, must be equal to, you guessed it, the weight force. It's equal in an opposite direction in order to be balanced if there is no friction present in this system. What this means is we can say, of course, that the centripetal force is equal to mv squared over r, as it usually is. That's also equal to the x component of our normal force. So that's the normal force, I guess, in the x direction. And we know that the other vector, the normal force in the y direction, is equal to the magnitude of the weight force. There really should be a negative sign there because it's pointing in the opposite direction, that's equal to mg. So if you're interested in figuring out what the magnitude of the normal force vector is, you would just use the Pythagorean theorem and these two values to figure out the magnitude of that normal force vector. Why do we care about all of this stuff, you're wondering? The reason we care is because we're interested in finding the perfect banking angle. The perfect banking angle is that angle such that the car will not slip even if no friction is present. It will maintain that circle without sliding down the hill or moving up the hill with no friction present just by having enough of a normal force. To figure out what that perfect banking angle is, we need to look a little bit harder at the relationship of the angle to the sides in the triangle we were just looking at. Let's start with looking at the edge-on view of the banked curve. This is the angle theta, our perfect banking angle. The diagram is going to be uncluttered. There won't be a car on it. I'm just going to draw our force vectors for you and put back on our axes. Okay, so let's start with our force vectors again. We have our weight vector down, acting on the car, F, W, there's a W there, and the normal force. We know, and these are probably not to scale, okay, we know that our normal force is perpendicular to the surface. And we're going to put on, again, our axes, x-axis, and the y-axis, which is going to be continued downward, of course, below here, okay? X-axis, y-axis. And let's now consider if we can figure out where theta is in the diagram in other places. Then, therefore, the relationship of the components of the normal force vector in terms of theta. Is this angle theta? Oops, wait, that didn't work. Okay, is this angle theta? No, we know that that's not the angle theta because we know that down here is a right angle, and so that must be the complement of theta. However, we know this angle is, in fact, theta. So our next question is, can we find theta in the triangle above? Is this angle theta? No, it can't be theta, because if we look carefully, we know that right, I better do this in a different color, red, here is a big 90-degree angle. Sorry, that's getting a little uncluttered, so let's get rid of that. Okay, instead let's just zoom in here and move this down a little bit. So we know that cannot be theta, so theta must be right here. How is that helpful? Well, it helps us because we know we've already thought about what the component of the normal force must be that lays along that y-axis. We know what that's equal to. We know that if we project this back perpendicular to the y-axis, that this component, this green vector, has a magnitude of mg, that's the weight. But also, notice its relationship to our angle, theta. Think about it. The relationship of Fn, which is the magnitude of the hypotenuse, the theta, the angle, and the adjacent side to theta. That's right, this has to be a cosine relationship. So you remember, of course, that the cosine of an angle, remembering SOHCAHTOA, is the adjacent side over the hypotenuse. So in this case, our adjacent side is Fn in the y direction over Fn. Okay. So that means that Fn in the y direction is also equal to Fn cos theta. We do that cross multiplication. So if that's true, and we also know what we said earlier, that Fn in the y direction is equal to mg, then the transitive property says, yep, mg is equal to Fn cos theta. Yep, it's right that you could be asking that. What's the big deal? Well, the big deal is we have not yet done anything with the x direction, right? So maybe if we look at that, we'll be able to see something pop up. All right, so here's a picture eliminating the y components of Fn and just showing you once again our centripetal force, our x component of the normal force pointing toward the center of the racetrack. If the y component was equal to Fn cosine theta, what do you think the magnitude of the x component is going to be? That's right. The magnitude of the x component has got to be Fnx must equal Fn times sine theta. And this is interesting, right? Because of course we said that Fnx is also defined to be, in this case, the magnitude of the centripetal force, which is mv squared over r. So transitive property again, mv squared over r, where, what is r? That's the distance from the bank to the axis of rotation on the racetrack, is equal to Fn sine theta. On the next slide, we're going to look to see if anything becomes apparent in terms of the relationship of the banking angle theta to, oh, let's say the velocity that we're going around the racetrack with and how far we are from the axis of rotation. Okay, so we said that Fn cos theta equals mg. And we said Fn sine theta equals mv squared over r. And what do you know? Something really cool can happen if we combine these two equations. And now, you might want to play around with them however you like, but what I like to do here, or what I see here, is that I can divide one equation by another. And it doesn't really matter what you put on top. I mean, it depends on, but your result is going to be, will vary. But let's just divide the top equation by the bottom equation. All right, and if you do that, let's take the left sides first. You'll see that, of course, the FNs are going to cancel out. We get cosine of theta over sine of theta is equal to, we have a compound fraction there, and you can do g over v squared times r. All right, so if you flip it over, you get sine over cosine is v squared over rg, and this whole thing over here is just the tangent. So it's independent of the mass of the car, and it depends on the velocity and how far it is from the axis of rotation, and that is your perfect banking angle.